Today I will be teaching you simple harmonic motion of an ideal spring. So first of all, what is an ideal spring? An ideal spring is a spring that has no mass, friction, or damping losses. Now, what is simple harmonic motion exactly, which stands for SHM? Simple harmonic motion is the motion of a mass that is oscillating, and oscillating means when the restoring force is directly proportional to displacement from equilibrium and opposite in direction. This is shown in Hooke's law. Hooke's law is f of s equals negative kx. I personally write f of x, however, it should be f of s. In this equation, k is the spring constant, which is measured in newtons over meters, and x is the position with respect to equilibrium, which is measured in meters. Here's the graph of force, which is measured in newtons, versus distance, which is measured in meters. This is a typical graph for an ideal spring that is in simple harmonic motion. As you can tell, the graph is linear and can be depicted by the equation y equals mx plus b. In these scenarios, the slope is typically the spring constant, unless given else. As shown before, spring constant is measured in newtons over meters, which makes sense here because the slope would be y over m, which would be newtons over meters. Now I will go over the work of an ideal spring. So the work is the integral of the force equation. In this scenario, it will be the integral from 0 to the final position of f with respect to dx. And because work does not have a direction, it is the absolute value. In this case, because f of s equals negative kx, the work equation will be 1/2 kx squared. Now we will go over the properties of simple harmonic motion. First, there's amplitude. Amplitude is the magnitude of the maximum displacement from equilibrium. This is measured in meters. As you can tell from the graph below, which is the position versus time, amplitude is given by the capital letter A, and it is the height of the crest from equilibrium. In this case, the equilibrium is at x equals 0. Next, we have the period. The period is the amount of time taken for the mass to complete one cycle. As shown below, the period is given by the capital letter T. Next, we have the frequency. The frequency is the amount of cycles the mass has traveled in 1 second. This is measured in hertz. As you can tell by the equation, frequency equals the inverse of the period. Next, we have the angular frequency, which is a similar concept. However, in this case, the angular frequency is the angular displacement of the mass after 1 second. Because of this, it is measured in radians per second. The equation for angular frequency is 2 pi times the frequency. Here is what the graph of the position versus time graph normally looks like for an ideal spring, as shown previously. And the equation for these graphs is x equals a, which is the amplitude, times cosine of omega, which is the angular frequency, times the time, plus phi, which is the phase shift / angle. Now, I will go over some commonly used simple harmonic motion spring equations. First, there's omega equals the square root of the spring constant over the mass. Now, we have the frequency equals omega, which is the angular frequency, over 2 pi, which is also equal to 1 over 2 pi times the square root of the spring constant over the mass. And now we have the period, which as shown before is the inverse of frequency, which is also 2 pi over omega and equals 2 pi times the mass divided by the spring constant. Now we will go over some practice problems. There's a mass which equals 1 kilogram that is hanging from the ceiling by a spring. If K equals 2.50 newtons over meters and the gravity is about 10 meters per second, find how far the spring is stretched from equilibrium. So, first, you should draw a free body diagram. In this free body diagram, there is a gravitational force that's acting downwards on the mass, and then the spring force, which is acting upwards. Because it is at equilibrium, the forces are balanced. Now, we will write the equation. Using Newton's second law, we have F net equals ma. which is also equal to Fg minus Fs according to our free body diagram. Because it is at equilibrium, F net also equals 0. Therefore, Fg also equals Fs. Now, if we expand that, Fg equals mg, and then Fs equals kx. Now, we will plug in our numbers. So, m equals 1.00, and then that is multiplied by 10, as given by the problem, which is also equal to 2.50 times x. If we do the algebra, x will equal 4.00 meters, which is the answer. Thank you for watching my video, and I hope you learned a lot about the simple harmonic motion of an ideal spring. Now you will take my quick quiz. Best of luck!